Hello everyone, today we're going to talk about pi. March 14th is Pi Day, and mathematicians all over the world celebrate it. To most people, pi is just a string of numbers starting with 3.14159. But if we look closely at nature, pi shows up everywhere. You can find it in the orbits of planets, the shape of an open umbrella, your heartbeat waves, and even in DNA structures. It almost feels like a secret numerical signature left behind for us by the Creator. Now, let's unlock the secrets of pi. In this episode, we will cover 3 topics. First, we will prove why pi is an irrational number. Second, we will look at 3 different ways to calculate it. Finally, we will see how pi appears in number theory and physics. The definition of pi is very simple. It equals the circumference of circle divided by its diameter. Whether the circle is a tiny coin or the huge Milky Way, this ratio never changes. Early civilizations tried hard to write pi as a simple fraction. Babylonian, Egyptian, and ancient Greek mathematicians all tried to calculate it using just 2 whole numbers, but they all failed. Finally, in 1761, mathematician Johann Lambert proved that pi is an irrational number using continued fractions. Later, Ferdinand von Lindemann took this a step further. He used proof by contradiction to show that pi is also a transcendental number. This means it cannot be the root of any polynomial equation that uses rational numbers. Let's look at a simple, one-page proof by 20th century mathematician Ivan Niven. We start by assuming the opposite. Let's pretend pi is rational and can be written as a fraction, pi equals a by b. Next, we build a polynomial function using only even-powered derivatives. Using calculus, we integrate the function f, x, times sin x from 0 to pi, which gives us a whole number that is 1 or greater. However, if we choose a large enough integer n, this integral becomes less than 1. This creates a mathematical contradiction. So, our first guess was wrong, which proves pi is irrational. Back in the 3rd century BCE, Archimedes used the squeeze theorem. He trapped a circle between an inside polygon and an outside polygon. As he added more sides to these shapes, their perimeters got closer and closer to the circle's actual circumference. He figured out the perimeter by repeatedly taking square roots using the Pythagorean theorem. Archimedes kept doing this until he reached a 96-sided polygon. Doing all of this by hand and in his head, his amazing work put pi somewhere between 3.1408 and 3.1429. Centuries later, Chinese mathematician Liu Hui created a similar approach called the circle-cutting method. He basically said that the more you cut the circle, the smaller the gap gets. If you cut it enough times, the polygon perfectly matches the circle. This idea is very close to the limit concept used in calculus today. Liu Hui calculated up to a 3072-sided polygon and estimated pi as 3.1416. Later in the 5th century, Zhu Chongzhi took manual calculation to its peak. Using only counting rods, he worked with a 24,576-sided polygon and found pi up to 7 decimal places, 3.141596. He also found the fraction 355/113, a world record that Western mathematicians didn't beat for nearly 1,000 years. But this geometry method has a big problem. Doubling the sides of the polygon makes the math much harder, but barely improves the precision of pi. Trying to calculate 100 decimal places this way would take a lifetime. Humanity needed a completely new way to compute it. Then, calculus came along in the 17th century and changed everything. Mathematicians realized pi could be written as infinite series. From then on, finding pi meant using formulas instead of drawing shapes. In 1593, French mathematician François Vite separated pi from geometry. He made the first infinite product formula for pi, using only nested square roots of 2. This formula was a huge milestone and the first to use ellipses to show infinite repetition. However, all those stacked square roots made it look pretty complicated. In 1650, English mathematician John Wallis found another infinite product for pi. His version didn't use square roots and had a nice, symmetrical pattern. In 1671, James Gregory and Gottfried Leibniz created another formula. It is a very simple alternating series. You just add and subtract the reciprocals of odd numbers to get closer to pi. But it is incredibly slow. Even after thousands of steps, you only get 3 correct decimal places. Finding 1,000 digits would take massive computing power. To speed things up, English astronomer John Mackin used Taylor series to create a much faster formula. Because fractions like 1/5 and 1/239 are small values, the series shrinks quickly. Mackin used his own formula to calculate pi to 100 decimal places. In 1914, the Indian math genius Srimivasa Ramanujan published 17 new formulas for pi. These formulas had incredibly fast convergence rates. Later, the Chudnovsky brothers built on Ramanujan's work and created the famous Chudnovsky algorithm. It is so fast that it gives more than 14 correct decimal digits every time you run a term. Thanks to this, modern computers can spit out billions of digits of pi in an instant. Calculating pi with geometry or calculus makes logical sense. But the next method might make you question probability and randomness. It's called Buffon's needle experiment, created by French naturalist Georges-Louis Leclerc de Buffon. Here is how it works. Draw evenly spaced parallel lines on a floor, with distance d between them. Then, randomly drop a needle of length L onto the floor. We just need to make sure L is shorter than or equal to D. We want to find the chance that the needle crosses any of the lines. To figure this out, we use 2 random variables. One is x. X stands for the vertical distance from the needle center to the closest line. Its range is from 0 to d/2. The other variable is theta. Theta is the sharp angle between the needle and parallel lines. It runs from 0 to pi/2. All needle drops happen randomly. X has uniform distribution from 0 to d/2. Its probability density function equals 2 divided by d. Similarly, theta follows uniform distribution from 0 to pi/2. Its PDF is 2/pi. X and theta are independent. We can therefore write their joint probability density function. Now, what is the rule for crossing a line? The needle crosses a line only if x is less than or equal to L/2 times sin theta. Since L is smaller than d, this math checks out perfectly across our entire range. We can find the overall probability by calculating the area where these conditions overlap. When we pull the constants out and do the math, the final probability is simply 2L divided by pi times d. So, let's test it out. Imagine dropping the needle n times, and it crosses the line h times. The ratio of h/n gives us the approximate probability. If we rearrange the formula, we can solve for pi. And if we make the needle length L equal to the distance d, the formula becomes much simpler. People have actually done this experiment throughout history. Buffon himself did the first test, and it went fairly well. Over the next 100 years, others tried it but only got rough estimates of pi with low accuracy. In 1901, Mario Lazzarini claimed to get a super accurate result, but many scholars thought he faked his data. The last recorded physical test was in 1925, but it failed to be very precise. In the computer age, this idea turned into the Monte Carlo method. Imagine a square drawn on a wall, with a quarter circle inside it. If you throw darts randomly at the square blindfolded, the chance of hitting the circle is pi divided by 4. Today, computers can generate millions of random points instantly. By counting the points inside the curve and multiplying that ratio by 4, we get a great estimate of pi. This isn't just a fun way to find pi, it is also a perfect demonstration of the law of large numbers. Next, let's see if pi appears in the world of whole numbers. Pick 2 large positive integers at random. What is the probability that they are coprime, meaning their greatest common divisor is 1? For example, 14 and 25 are coprime. Euler proved this probability equals 6 over pi square, roughly 60.79%. Integers are discrete and rigid, while pi is linked to curves and continuity. It seems they have nothing in common. How could they be connected? This mystery traces back to the famous Basel problem, which centers on the Riemann zeta function. The derivation is straightforward. For any prime number p, the probability that a random integer is divisible by p is 1 over p. The probability that two random integers are both divisible by p is 1 over p square. Thus, the probability that they are not both divisible by p equals 1 minus 1 over p square. This is basic high school probability. Since divisibility by different primes are independent events, we take the product of these terms over all primes to get the probability of two numbers being coprime. How do we work out this infinite product? Here comes a brilliant connection. Euler's product formula elegantly links this infinite product to the Riemann zeta function. When s is equal to 2, the product equals exactly 6 over pi square, which is the coprime probability we are looking for. Pi acts like a messenger across different fields, weaving geometry deep into number theory. Since pi turns up everywhere, can we find it in the laws of physics? In 2003, mathematical physicist Gregory Galperin published a research paper. Consider perfectly elastic collisions with no friction, where energy and momentum are strictly conserved. Place a large block of mass m and a small block of mass m on a frictionless flat surface, with a wall on the left side. As the kinetic energy of the large block gradually dissipates, it eventually stops and rebounds to the right, moving away from the small block. The collisions then come to an end. The detailed process is as follows. Let's demonstrate the process. First, if the two blocks have equal mass, they collide 3 times. When the mass ratio is 100 to 1, there are 31 collisions. For a ratio of 10,000 to 1, the number of collisions rises to 314. If the ratio becomes 1 million to 1, we get 3,141 collisions. The key secret lies here. When we plot the velocities of the two blocks in a phase-space coordinate system, the law of conservation of energy forms a perfect circle. Every collision corresponds to geometric reflection on this circle. Some may wonder, even for measuring the circumference of the observable universe down to the scale of atoms, we only need the first 40 decimal places of pi. Why spend so much electricity calculating trillions of digits? In engineering, computing pi serves as an ultimate stress test for supercomputers, helping evaluate performance and detect hidden hardware bugs. A machine that calculates billions of pi digits flawlessly guarantees stable CPU, memory, and cache performance. Philosophically, this pursuit reflects humanity's innate urge to explore the unknown. Pi is far more than a property of circles, it is deeply embedded in the fundamental rules governing our universe.